Let us look at proposition number 9 of works of Archimedes, specifically from book 2 of On the Sphere and Cylinder. The proposition says, of all segments of spheres which have equal surfaces, the hemisphere is the greatest in volume. So let's understand this step by step. Let A be A prime B prime be a great circle of a sphere. A prime its diameter and O the center. Let the sphere be cut by a plane not passing through the center O, perpendicular to A prime at M. So let's bring in that plane, and here the intersection of this plane with the great circle is at B and B prime, and it intersects the diameter A prime at M. Let D prime E prime be a great circle of another sphere. D prime its diameter and C the center. Let the sphere be cut by a plane through C perpendicular to DD prime and intersecting the great circle in the diameter EE prime. The plane is intersecting the great circle at EE prime. Of course, it is intersecting the diameter at C, because that is where we drew the perpendicular plane. Now that you have got the idea of these planes cutting these, so let me hide it. Take R on A prime such that AR square is equal to AB square by 2. Okay, so this point R we have taken such that AR square is equal to half of AB square. So let me draw AB. Let us join BB prime and EE prime and DE. Produce OA prime to K such that OA prime is equal to A prime K. Produce AA prime to H such that A prime K is to A prime M is equal to HA is to AM. So here you will notice we know A prime M, we don't know HA, but we do have AM and A prime K. So only one unknown. So which means we can easily find it. Produce CD to F such that CD is equal to DF. So here what the proposition is saying is, if the surface of segment of sphere ABB prime, segment of the sphere, what do I mean by that? This part of the sphere, its surface area, if it is equal to the surface area of this segment, then since it passes through the center, its volume will be greater than the volume of this segment. Since we have constructed it in such a way that the surface of segment of sphere ABB prime is equal to surface of segment of DEE prime, that means AB is equal to DE. Now, AB square is greater than 2 times AM square. AB square is greater than 2 times AM square. How do we arrive at that? Because remember, BM is greater than AM. Since AM is less, BM is greater, that means AB square, which is the hypotenuse because it is a right angle triangle, AB square is equal to BM square plus AM square. So instead of BM, which is the greater, if we take AM square 2 times, then AB square will be greater than 2 times AM square. And AB square is less than 2 times AO square. Again, we can see that this is true by joining A prime B. So now AB square is greater than 2 times AO square. Remember, we took R on A prime such that AR square is equal to AB square by 2. And because of these inequalities, R will fall between O and M, since AR square is equal to AB square by 2. Since AB is equal to D, the squares on them will also be equal. So AR is equal to CD. AR is equal to CD. We did this construction. A prime K is to A prime M is equal to HA is to AM. So I'm taking it here. Now I'm doing componendo. A prime K plus A prime M is to A prime M is equal to HA plus AM is to AM. Now A prime K plus A prime M is KM is to A prime M is equal to HA plus AM is HM is to AM. So which means cone HBB prime is equal to segment ABB prime. Segment of the sphere ABB prime. Cone FEE prime is equal to the hemisphere DEE prime. So now what we have to do is we have to show that the volume of this cone is greater than the volume of this cone, which will mean that the volume of this hemisphere is greater than the volume of this segment of the sphere ABB prime. So let's begin. AR times RA prime is greater than AM times A prime M. How did we arrive at this? AR is to AM is greater than A prime M is to A prime R. Now we are doing dividendo on this. AR minus AM is to AM is greater than A prime M minus A prime R is to A prime R. Now AR minus AM is RM. Similarly, A prime M minus A prime R is RM. So which means we get RM is to AM is greater than RM is to A prime R. So what Euclid would call antecedents, they are the same in both these two ratios. AM is less than A prime R. How? Because AM is less than the radius and A prime R is greater than the radius. AM is less than A prime R. That means RM is to AM is greater than RM is to A prime R. So that is how we arrived at this. AR times RA prime is greater than AM times A prime M. AR square is AB square by 2, which is how we constructed it. AR square is equal to half of AM times AA prime. Did we get this? AB square is equal to AM times AA prime. This we are getting it from a lemma from Euclid, book 10, which means AR square is equal to AM times A prime K. Because A prime is the diameter, A prime by 2 is the radius, and A prime K has been constructed equal to the radius. Here we have AR square, here we have AM times A prime K. On this side we are adding AR times RA prime. On this side we are adding AM times A prime M. Here you have an equality. But the moment we add AR times RA prime on this side and we add AM times A prime M to this on this side, it becomes an inequality. This left hand side becomes the greater than the right hand side. And here if you notice, AR is common. So AR, we take it out and we get RA prime plus AR is greater than, here AM is common. So AM times MA prime plus A prime K. RA prime, RA prime plus AR is AA prime. So we have AR times AA prime is greater than AM times MA prime plus A prime K is MK. AR times A prime is greater than HM times A prime M. Since Km is to A prime M, Km is to A prime M is equal to HM is to AM. Km times AM is equal to HM times A prime M. So we can substitute AM times MK with HM times A prime M. Now AA prime is to A prime M is greater than HM times AR. So this multiplication we have converted into ratios. AA prime is to A prime M is equal to AB square is to BM square. So we are again substituting it. Is greater than HM is to AR. AB square, remember, is AB square is 2 times AR square. So again, instead of AB square, we are writing AR square. But 2 times here, instead of taking it here, we are taking it in the consequent on this side. So AR square is to BM square is greater than HM is to 2 times AR. So AR square is to BM square is greater than HM is to CF. How did this CF come? Because remember, 2 times AR, we are substituting it with CF. So let's look at AR and CF. AR is equal to CD and CD is equal to DF. So CD, DF. So which means 2 times AR is equal to CF. So what does that mean? It means circle on diameter E prime is to circle on diameter BB prime is greater than HM is to CF, since AR is equal to CD or C. In turn means cone FEE prime is greater than cone HBB prime. Remember, circle on diameter EE prime is the base of this cone and CF is the height of this cone. Whereas here, the circle on diameter BB prime is the base of this cone and HM is the height. So because of this inequality, we can say cone FE prime is greater than cone HBB prime, which in turn means what? Remember, cone FEE is equal to the segment of the sphere DEE prime, which is a hemisphere, and cone HBB prime is equal to the segment of the sphere ABB prime. So that means hemisphere DEE prime is greater than segment ABB prime. So what we have proved is that if we have two spheres, each of them cut by planes, such that one of them is cut not through the center and one of them is cut through the center of the sphere, then if the surface areas of these segments are equal, then the one which goes through the center has a higher volume or the greatest volume. So as the proposition says, of all segments of spheres which have equal surfaces, the hemisphere is the greatest in volume. Now here again, I have done it in such a way that you can actually see this. If I increase the size of this, you notice the surface area of this increases, of this hemisphere. Accordingly, M shifts to maintain the equality of the surface areas. So this was a case where M was on this side. Similarly, we can prove it for if the M is on the other side. So accordingly, a little bit of these conditions will differ, but otherwise the proof remains the same. So that is proposition number 9 of works of Archimedes, specifically from book 2 of On the Sphere and Cylinder. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.